let's start today with separable differential equation. Now, to understand what this is, let's start with something like y squared equal to x. And I hope you remember how to do implicit differentiation. Let's try to do an implicit differentiation of this thing. So if I differentiate both sides, each differentiated, y squared, I'm differentiating with respect to x, right? So x differentiates to what? X differentiates to? 1. Okay. What do you get if you differentiate y squared?
Get 2y.
It's y is a function of x, and I'm differentiating with respect to x.
Oh, you get
2y prime. So somebody remembers the implicit differentiation. Okay, now if you're still not sure, I think many of you were used to remember. I mean, many of you were taught implicit differentiation as differentiation with respect to x in leafless notation. This is the leafless notation, right? And you probably learned it something like you want to differentiate y squared by dx, but because x and y doesn't match, you put dy, but instead you put dy over dx here. Differentiating x by x, that's just 1, that's not a problem. But see, once you rewrite d over dx as d over dy and put dy over dx, and this one I know that it's 2y. If you differentiate y squared by y, you get 2y. And dy over dx is dy over dx. Okay? So some of you may have seen the implicit differentiation in this format, and that's probably why you weren't able to answer it like this. But anyways, this is what you get if you differentiate using implicit differentiation. Okay, now let's try to solve this for y prime. Y prime equals to 1 over 2y. I mean, you can also solve this for dy dx. And same story, right? Y prime means dy dx. This is just a different notation for the derivative. This is called the Leibniz notation. This is called Newton's notation. Now, what I'm trying to ask you is, isn't this a differential equation? It is, right? It's a differential equation. It has a derivative and some function, and you're trying to solve this for y. You want to find the function y which satisfies this. And I want you to see that this is actually exactly the same. If you solve this, one of the solution must be this one. How is that? Does that also make sense? Because where did we obtain this from? From here. We differentiated to get this one. So this must be one of the solutions. Now, this is not all the solutions because there could be some constant plus c here, which if you differentiate will go away. So probably if you solve this, you're going to get y squared equal to x plus c. So this is just one of the solutions. And then, since this is equivalent to saying that y is equal to square root of x or y equal to negative square root of x, what you have here is you have a differential equation whose solution contains square root of x and also negative square root of x. Either one of these should be a solution. Okay? That's what I am. All right. So now here's the question: where? How do you solve this? And I mean, I could have just posed you this question to begin with and say, hey, here's the differential equation. This is called a separable equation. And if you solve it, you get this as the answer. But it kind of gives you more insight into what's going on if you actually have your solution known before you solve it. So let me show you how this is solved. Okay. All right. So this is like in the back of your mind. For a moment, let's just say that something happens here that it's supposed to be kept as a secret, and let's say we were given this question. Here you have a question where you're given y prime equals to 1 over 2y. What is the solution? That's the question. Now, to solve this, maybe the way, because we start from here and got this, solving something is just the opposite of what you're doing, right? So maybe the right way to do it is to go backwards and see what happens, right? Okay, so what should I do first? Looking at this, what should I do first? Yes, I should multiply by 2y, which gives you 2y, y prime, equals to 1. And then I need to go from here to here, y squared equals to x. So what should we do in the next step? Integrate, because we differentiated, right? We differentiate to get this, and what's the opposite of differentiation? Integration, right? So of course we want to integrate. So we're going to integrate both sides.
Now, what would tell you to integrate with respect to x? Just looking at that original
okay, well, I mean, this itself means it's the derivative with respect to x. Right? Even if it doesn't tell you explicitly, you should consider this as, well, y is a function of some variable, right? I mean, you could say y is a function of t, and there is some ambiguity here because there is no explicit variable that's in here. I mean, if you want to be explicit, you might actually say y is a function of x and y is a function of x and write this x implicitly. But because we understand y is a function of x, we would differentiate it and we would integrate by dx. Yes?
If you're in that other form, can you cross multiply to get that?
Cross multiply to get this.
In the dy dx?
Yeah.
Okay.
You're right. Okay. So we integrate. Now the right side is easy. What do you get if you integrate 1? X plus c. By the way, when you integrate both sides, you only need to put plus c on one side. Okay? Because all you're saying is that the two functions differ by a constant. Okay. Now the next question is, what is this? What's the integral of this?
Y squared.
Y squared. And thus we've solved it. This is the solution that we started with plus c, which is addition. If you want to see, differential equations has the goal of finding the function which satisfies this. So often, if you can, you're advised to solve for y. So if we solve for y, we get y equals to plus or minus square root of x plus c, which definitely contains these two cases. These are the solutions of this differential equation. Okay? But actually, if I didn't tell you what's going on here, there's a part where a lot of you will be lost. And the part that you're going to be having trouble understanding is, how did this integral become y squared? So let's think about that a little bit. Okay? Well, it's basically a u substitution, right? Because if you set y is equal to u, then what is dy? No, sorry, that's not how you. See, these are function of x. So you're basically saying that u is the y, which is the function of x. And therefore, if you want du, it will be y prime x dx, and dx would be 1 over y prime of x du. And then if you replace this integral as integral of 2u and then y prime of x times 1 over y prime of x dx, sorry, du. Maybe I should circle here. Maybe get the color pen. So what I'm trying to say is that dx is this much, right? And because that's what we said, right? And then y prime is just y prime, same thing. I just explicitly wrote down parenthesis x to say that it's a function of x. And once you write it like this, you see that these cancel, and you end up with integral of 2u du, which is u squared. And then because u is same as yx, you end up with 1 squared. Okay. So we see that basically what's going on the left side is a u substitution. Now, I only did that so that you can familiarize the reasoning behind this integral, but actually there's a shortcut which is much simpler. Here's another way to think about it. And it has to do with the leafless notation. If you write down y prime as dy dx, as in leafless notation, here's the power of the leafless notation. You don't have to go through all that. You can just say, hey, here's dx, that cancels. I'm integrating 2y as a function of y. So what's the integral? Y squared. Done. Very simple. Yes? Isn't that simple?
Yeah.
Yeah, it's much simpler, right? Okay. And let me show you the most simplified version. And then you will understand why I'm calling this section as separable equation. So again, if the question is y prime equals to 1 over 2y, and you're asking what's y prime, here the simplest solution is the following. Step 1, if you have to, rewrite using the leafless notation, because leafless notation is much better at doing these questions, okay? And then, what you want to do is, if you can, move all the x's on one side and move all the y's on the other side by multiplying. Not by adding or subtracting, by multiplying. Can you move things around so that this goes to the other side, this goes to this side, which is something that you said, it's the cross multiplication. You can do the cross multiplication here. So if you cross multiply, it's not always the cross multiplication, but here at least it's cross multiplication. All right, so you have 2i dy equals to 1 dx. Right? And then, once you sort out only the y's on one side and x on the other side, you integrate. And now the left side is y squared, right side is x plus c. You just have to put c on one side, and that's it. That's the solution. Of course, you want to solve for y, so it's y is plus minus x squared plus c. Okay. And such a differential equation is called a separable differential equation.
It would just be x plus c.
Thank you. X plus c, not x squared plus c. It's called the separable differential equation. Now, I could have just shown you this in the beginning and not explained further, but if I did that, a lot of people will be uneasy about how you can suddenly think of this as a fraction and move this to the other side. What's really going on is I'm not really multiplying this to the other side. Rather, what's happening is at this stage, so you can kind of skip this step and say, at this stage, I'm integrating both sides by dx. That's what's going on. And when you integrate both sides by dx, the dx's cancel, leaving you with integration by dy on the left side and integration by dx on the right side. But often it's explained this way because it's easier to think of it this way, and plus it's easier to keep track whether you have all the y's on one side and x on the other side. So this is the standard way that separable equation is taught. Any questions?